Good evening, everybody, and welcome to Advent of Code Day 10. As usual, we program everything in Go. So, let's start directly with the puzzle, I think. So, there's nothing important to say. So, okay, Day 10. Cathode ray tube. You avoid the ropes. Ropes. There's actually something. Yeah, maybe at the end. You avoid the ropes, plunge into the river, and swim to shore. The elves yell something about meeting back up with them upriver. But the river is too loud to tell exactly what they are saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritized getting the communication system on your handheld device working. You pull it out of your pack, but the amount of water slowly draining from the big crack in its screen tells you it probably won't be much of immediate use. Unless, that is, you can design a replacement for the device video system. It seems to be some kind of cathode ray tube screen and simple CPU that are both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. Start by figuring out the signal being sent by the CPU. The CPU has a single register, X, which starts with the value 1. It supports only two instructions. Add XV takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. Okay. And no op takes 1 cycle to complete. It has no other effect. The CPU uses these instructions in the program, your puzzle input, to somehow tell the screen what to draw. Considering the following small program. No op at x3 at x minus 5. Execution of this program proceeds as follows. At the start of the first cycle, the no-op instruction begins execution. During the first cycle, x is 1. After the first cycle, the no-op instruction finishes execution, doing nothing. During the first cycle, x is 1. Why is that? The CPU has a single register X which starts with the value 1. It supports, okay, this is just a register, so it doesn't, X doesn't change without any add. Okay. At the start of the second cycle, add 3 instructions begins, the add 3 instruction begins execution. During the second cycle, X is still 1. Of course, because in the second cycle, at X takes 2 cycles, so therefore at the end of the first of those 2 cycles, it's still 1. Okay, during the third cycle, X is still 1. Okay, while it's still ongoing. After the third cycle, the add 3 instruction finishes execution, setting X to 4. Okay, then at the start of the fourth cycle, the add X minus 5 instruction begins execution. During the fourth cycle, X is still 4. Okay. During the fifth cycle, X is still 4. After the fifth cycle, the add X minus 5 instruction finishes execution, setting X to minus 1. Okay, maybe you can learn something by looking at the value of the X register throughout execution. For now, consider the signal strength, the cycle number multiplied by the value of the X register during the 20th cycle and every 40 cycles after that. That is during the 20s, 60s, 100s, 140s, 180s, 220th cycle. For example, consider this large program. Okay. The interesting signal strength can be determined as follows. During the 20th cycle, register X has the value 21. So the signal strength is 20 times 21 equals 420. The 20th cycle occurs in the middle of the second at X minus 1. So the value of the register X is the starting value. 1 plus all the other at X values of that point. 1 plus 15 minus... okay, these are the operations that are happening, okay. During the 60th cycle, register accessor value 19, so the signal strength is okay. Signal strengths get higher. Some of these signal strengths is 13140. Find the signal strengths during the 20s, 60s, 100s, 140s, 180s, and 220s cycle. What is the sum of these 6 signal strengths? Okay, this doesn't sound too bad. Okay, so basically what we need to implement is then basically just an interpreter for these small programs, right? So, and this means basically we have 2 different commands. We have this no op and we have this at x. So, and then within our program or within our interpreter, we have the value or the cycle number. So basically every command takes a limited amount of cycles, and after those cycles are done, the next command can be processed. So, and then we also have this variable x, and cycle number plus times x, or what was it? Is the signal strength. Cycle number multiplied by the value of x is the signal strength. Okay. Good. This seems to be doable. So we have some nice tests here. So these are things that we can all test, where we can just print out the values and then see if these values basically match what are given here. So this should be quite doable. Let's see. Okay, first start, we just copy our test program. This should be doable. Oh, maybe we already have 2 programs, right? Yeah, we have also the small one. Maybe we start with the small one. And then we can test all those 5 properties. Okay, so let's start with the small one. Copy it over to our new project, test1.txt. So we have also some new file. Oh, we have some new file, test2.txt, and this will then contain basically the larger test program. Okay. And then basically just start coding. So we have our new application that is called date10. Yes, and we want to edit. So let's think about what do we have. Basically, we have our commands. So we have a command that is basic, or the interface type command. And what does the command actually do? So basically we can just execute it. But then the question is, what would be the result of it? So somehow this execution need to influence the state of the interpreter. So therefore we can do it in 2 different ways, right? We could basically give the execute method the context. So where we just say what it should do. This would be probably the best thing. The only question is, for example, how do we implement these things about how long a command actually takes? So for that, we can basically ask for, okay, get cycle time. So each command has a specific cycle time. And when we execute it, what happens basically, it returns a new value. Let's say basically it returns just a new value that changes x. So basically we just return an int, and this should be it. And our cycle time should also return an int. Okay, then we have different things. We have a command which is basically the no-op. Yeah, and no-op basically does nothing, so therefore implement the methods correspondingly. So we have our no-op, and we have the cycle time int, and basically what it does is just return 1, because as we, at least I think, that it should be 1 cycle that a no-op takes to calculate. So then we have execute, and there basically we should maybe give also int as an value. So where we say we have our x value and then basically we return the modified x, and this will be just, we return everything x without modification at all. So therefore we return it as it is. Okay, then next, the other operation that we have is basically our addX. And addX has also a second parameter, which is basically the value. I think it was called value. The value. So, and the cycle time of addX was basically 2. And execute does the following thing. It takes the current way of x and then just returns x plus a dot value. So not too hard, not too complicated. So these are basically the two different operations that we can find in our program. So let's check back with the browser. So now we can try to implement some parsing for that, and then we will run these tests and see if basically our small program returns or holds all those properties that are basically mentioned here. So what do we need to do? We need to check, maybe we, after every cycle, we just print out x. So because this is here basically where we say second cycle x is still 1, third cycle it's still 1, and then basically afterwards in the fourth cycle it's 4. Afterwards we're setting it to 4, and then at -5 is, and in the fifth cycle it's still 4, and after the fifth cycle would be the sixth cycle basically, then this -5 is executed, so it gets -1. Now, these are things that we can also easily check by printing out the cycle, or each cycle printing out the number of the cycle and the value of x. And then we should be able to see if the calculation is correct. Okay, so but for that, first going back to coding and start with our usual boilerplate code where we need to read the input data. So open test1.txt. We start directly with our shortest test file, which doesn't contain that much information. Okay, if we have an error, just panic. No, not just panic. This is the easiest way to handle it. Why is this a problem? If in not equal nil. Okay. So we need to close our file when we are done. Okay. So, and as usual, these are line-wise data, line-wise formats. So therefore we use our buff.io scanner and create the scanner to basically be able to read it line by line. And scan, and then line is equal scanner.text. Okay, now we need to pass the individual commands, right? Where we have our where we now have our method that returns that. This is something that we can now build. Pass command, which takes a line or a text, let's say, just line. Assume it's a line-based programming language, which is actually is. So, and what we do, we basically return a command. Okay, so within those, we basically have two different cases. So first, if line or command string equals, and then if it's no op, this is quite easy. This is the easiest case. We just return no op command. Else. Now we check if the command string starts with @x. If command string, and now how can we check if something starts with? So let's see if there is some method for that. Starts with or begins with first. Now index of we can check this. I think this should work. We say is the index of our substring at x with a blank, just to be safe. If the index is equal 0, because it would be directly at the beginning of this, else if, then basically we can be sure that what comes afterwards is just the number. So we can then just try to get our value out of it. So value will then be command string, and then we split it after, we only take the part that comes after the 5th symbol. So basically 0, 1, no. Yeah, the 5th including. So 0, 1, 2, 3, 4, and then 5. This is the 5th, including the rest. So, and this is then basically what we will pass. So, since this should be an integer. So, a to I. If error, then again, just panic. So, and now that we have the value as well, we can just return @x, @x command with the value equal value. So, and in the other cases, I would maybe we don't. Maybe we actually return an error. I think it's quite it's more appropriate to return an error if something is wrong here, and not just panic every time. Because here this is something where we want to tell the user that, or someone who actually writes the program, hey, what you have written is not correct. So therefore, is there some command that we can, or can I create nil and then error? No, this doesn't work as well. Oh, it does. Okay. There we create nil as an error on them. This is fine. And if we don't match, this means we have an unnamed, and basically we have an, yeah, let's say we have some command that we don't understand. So therefore, we should print out a message for that. Unknown command. Comma, and then we just take the command string. Okay, so this for the part where we get our command. Command equals parse command from line. And we also get an error, and if we have here an error, then basically within our main we don't have anything else that we can do except for panicking, therefore just panic, and then this is fine. Okay, so much for the command. So now it's about changing the cycle, right? So, or calculating the cycle time. So we begin with a cycle time, or cycle, yeah, time that is equal 1. At least this is what I got. And we have the value of our interpreter, which will be x. And x is equal 1, if I remember correctly. Let's check again with the which start with the value x. And then at the start of the first cycle, the no-op instruction begins execution. After the first cycle, the no-op instruction does doing nothing. Okay. Good. So I think this is correct. So we just assume that we start as the first cycle. So then what we are now doing is basically we have our command, and then based on the command we need to, yeah, make changes. No? We need to execute them. So therefore, first we need to check how long these commands take. So, and we need to wait accordingly, right? So therefore we do something like that. For e equals op. Then wait cycles. Wait cycle. In 0, so we start with 0 wait cycles, and wait cycle needs to be smaller than basically our command dot cycle time. So we need to go, and we have then wait cycle plus plus. So basically we loop through this command to wait for the cycle that those commands take. So within this we just increase the cycle time by 1. This doesn't look that nice, and we could actually do this easier in one loop, but okay, I think this should give us the end. So this should take care of the cycle time, so that we know at the end of the cycle time basically yeah, how long the command took. So then comes the important part. Now the command is still is finished with waiting, but we are still in the cycle, right? So therefore we need to print out what is actually the cycle here. the point is we need to wait with the execution until we have printed out everything. So, for example, take this example. During the third cycle, x is still 1. So after the third cycle, the x instruction finishes executing, setting x to 4. Oh, but this means this is after the third cycle, so within the fourth cycle already. So therefore, what we print out, we need to be careful when we print out basically what is the current state within the cycle. So therefore, we just do something like that. Yeah, we just print it out here. Format, print, print cycle d x equals %d. And then we print out cycle time and our x value. Okay, so and then when we have printed these things out, we can apply the what the command actually needs to do. So we put in x and we assign this back to x, so that our command has the ability to change its value. So now with this, basically we can just try to run it and see what happens. I think we are currently running something else. This doesn't sound right. Yeah, we are running day 9, which is completely wrong. So let's run and say go build day 9, day 10. Okay, so let's compare this. So cycle 2, x is equal 1. Cycle 3, x is equal 1. Cycle 4, x is equal 1. Does this make sense? I don't think so. So at the end of cycle, we should start by cycle 0 because, okay, now it looks better. So basically our, oh, did I already miss it? Okay, so basically we go through, yeah, basically we have this loop here where we wait for the time that each command takes. We print out in which cycle we are and the current value of x, and then basically we execute x, and after those cycles have been done. And then we go to the next command and continue basically. And this gives us then the output that we see here. So where we have cycle 1, x is equal 1. Cycle 2, x is still equal 1. Cycle 3, x is still equal 1. Because within cycle 3, the result of this add 3 operation hasn't finished yet. And then basically we should also print out this at the end. And this is then basically the next cycle. Cycle time plus. So this is basically then the final state. So we also need to look at the final state, and the final state is basically that x is -1, and then basically our program is halted. So this cycle is not really there. So, okay, let's compare it. During the 5th cycle, x is still 4. After the 5th cycle, the add -5 instruction finishes execution, setting x to -1. So this looks basically like we are basically calculating the correct things, which is quite nice. Okay. So let's now see what has to happen with the larger problem. I will copy these things over to a new file so that we can have this here directly when we are programming as well. Let's create a new file that we call test result, test2.result. No, we don't want to add that. And this is basically just the description of what we expect. Okay, then let's see what happens when we now run it on test2. Okay, so we have here 241 as the last cycle time. And there's a couple of things. So let's check basically what we have. So cycle 20, begin with cycle 20. Cycle 20, x is equal 21. During 20 cycle register, x has the value 21. So the signal strength is 20 times. Okay, signal strength is something that we currently don't have, but this will be implemented then as a follow-up. Okay, so let's look at the next cycle, which will be 60. Cycle 60, x is equal 19. 19. Okay, sounds correct as well. Cycle 100, x is 18, x is 18. Okay, so far I think the interpreter seems to work. Cycle 140 will be 21, cycle 180, 16, also correct, and 220 will be 18. This is also okay. Okay, so we know that our interpreter works correctly now. So now it's a problem that we need to figure out how to calculate the signal strength. But the signal strength shouldn't be that hard, right? So basically the signal strength depends only on our cycle time and x, so therefore we can just calculate it. So, and now let's do this. So basically create a function which we call calculate signal strength, and it takes the cycle time, which is an integer, and it takes the, yeah, I don't know, the x, just the x, and it returns again some integer. So therefore calculate cycle time. Let's scroll up to see how exactly. I think it's just multiplication, right? Let's consider, no, it was, the integer string can be determined as follow. So the signal strength is 20 times 21. Yeah, okay. So back to coding, so it's just multiplication. Okay, maybe it wouldn't have been necessary to create a new method for it. But okay, who does know? So, and now we can also calculate this every time. Cycle signal strength is equal calculate signal strength, cycle time, and x. And signal strength is something that we defined before, so this is something that we will have also throughout the whole program, so therefore we can reuse this here. And we also calculate this at the end. Not that we need it there. Okay, and then we also print it additionally here as well. Signal strength is equal %d, and then again signal strength. Okay, let's execute it, and then we will compare basically the signal strength that we calculated with the signal strength that should be here. So can we move this to the here? Maybe go here. So, okay. Let's start with the 20th cycle. 20th cycle will be 420. 420. Okay, correct. Then the 60th cycle will be 1140. Okay, correct. Next will be the 100th. That will be 1800. Also correct. 140. 2940. Also correct. 288, 180 is 2880, correct, and also okay. So basically, calculation of our signal strength is also correct. Nice. Okay, now the problem is we need to calculate or capture the cycle time at specific values or at specific cycles. So, and this is basically that. And we only do this at specific cycle times. So therefore, we we need to do that at the 20s, 60s, 100s, 140s, 180s, and 220 cycle. Okay. What are the sums of these six signal strengths? Okay, this. So for that, we can create something that basically just checks if the signal strength should be summed up or not. So we have this. How do we do this? So every time basically we calculate the signal strength, we should also basically be able to capture its value. So so that we can sum it up if we are in the corresponding cycle times. So let's call these things. What do we have? I would think it's maybe something that is related to the program or to the protocol. So therefore we can say we have our protocol, which is basically the thing that decides when to capture the individual cycles, the individual signal strength. So our signal or radio protocol or whatever you can call it, and this has in the end the signal strength sum. And then basically this is just an int. And it gets a new method that we then call func p protocol. And yeah, well, what does it do? It basically reads, let's say it reads the signal. And this takes the current cycle time. And it takes the signal strength. And currently we can hard code this. So if cycle time in, not in. Yeah, how do we do this easier? I have the, okay, maybe we just hard code this for now. If cycle time equals 20, or cycle time equals 60, or I think there are just 6 values at the moment, so therefore, and we can always come up with something smarter in case we need to change this for part 2. 140, or maybe we can already do here the break. Cycle time equal 180, or cycle time equals 220. So if we know we are in these cycle times, then we basically take the single strength and add them to our sum. So we do something like that. We do P single strength sums plus equals our single strength. So, and now we have our protocol that we also create here. Protocol is the new protocol. And every time we calculate our signal strength, basically we just update the protocol. Protocol read signal from our cycle time and our signal strength. So we do the same also here, but I think this should not be necessary. But okay, and now in the end we can print our complete sum format .printf signal strength sum is protocol.signal strength sum. Okay, run it, and we see our signal strength is 13,140. Compare it to what we have here. Okay, it's the same. So therefore, I think we can try to run it now on our input data and see if we come to some value that works. Run it. Oh, the file can't be specified. Oh, we didn't get it yet. Okay. Yeah, so request our input, of course. Get our input file. Here it is. Copying over up to the browser and create our new file. Input.txt. Yes, we can edit. Okay, it's not that large, the program. 142 operations. So I think this is nice. Just run it and we see our cycle signal strength sum is 13,480. Okay. Good. Then let's try if this is the correct answer. 13,480. Submit and yes. Okay. Part 1 is done. Correct. They're really nice. So now it seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide and the X register sets the horizontal position of the middle of that sprite. Okay. In this system, there is no such thing as vertical position. If the sprite horizontal position puts its pixel where the CRT is currently drawing, then those pixels will be drawn. You count the pixels on the CRT, 40 wide and 6 high. The CRT screen draws to the top row of pixels left to right, then the row below that, and so on. So every time in this, and this, and this, and this, and this. Ah, okay, and there. This is how we come to the individual cycles. So then the row below that and so on. The leftmost pixel in each row is in position 0. The rightmost pixel is in position 39. Like the CPU, the CRT is tied closely to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as a hash. Here are the cycles during which the first and last pixel in each row are drawn. Okay, makes sense, right? So with every cycle, basically, we move one to the right, and then when you are at the end of the row, you start over one row below. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel. Otherwise, the screen leaves the pixel dark. Okay, the first few pixels from the larger example above are drawn as follows. Sprite position hash 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 and then start cycle 1, begin executing at x15. During cycle 1, CRT draws pixel in position 0, CRT 0. Finish executing x15, sprite position is there. Begin executing -11. Ah, okay, so the sprite starts here. So therefore, at the beginning, when x is 1, it's looking at the position. So basically, it's finding the sprite in this position, and therefore it's printing out. So now the cycle time goes one step further. So it checks is 1 pixel of the sprite, or if the current cycle time is within the sprite, that one of its 3 pixels is the pixel currently being drawn. Wait a minute. X controls the horizontal position of a sprite. It's 3 wide, and X sets the horizontal of the middle of the sprite. Okay, this means that this would be... Okay, this is cycle 1. But then X, what is X in this? X is 1. But then the middle should be 1. Then this is not correct. The leftmost is in position 0. Ah, okay. Okay. The leftmost pixel is in position 0, and the rightmost pixel in each row is position 39. Okay. That makes sense. Okay. So this means the sprite is in position 1, because this is 0. Okay. So therefore, in this position, the CRT draws. Okay. Then basically after that, we jump, or the sprite position changes. So, and therefore, in the next step, this pixel is not lit. So then basically there is this at x -11, draws pixel in -3, so which also takes 2, and then basically this position changes. Then again we draw the pixel at 6, so it doesn't draw because it jumps away after 2. Then basically it goes -3 again. Okay. I think I understand. Allowing the program to run the completion causes the CRT to produce the following image. Render the image given by your program. What 8 capital letters appear on your CRT? Okay, now we need to write a renderer for that. Okay, sounds fun. What 8 capital letters appear on your CRT? Okay, so this means that in the end we must... Is this the only drawing? Ah yeah, we render only in 240 cycles, so therefore this is basically what we... Okay. Yeah, not a problem at all, I think. Okay, going into the code. So this means if we need to render the X position, then we should probably need the single strength? No, we don't need it at all. But okay, we can leave it in. We just don't need to print it. So every cycle we need to update our display. So for that we write something like this, where we just print out within our display display or show render pixel. Let's say render pixel. And this render pixel also get the, oh no, not this, but the cycle time. It gets the current cycle time. And it gets the value x. So to determine if something is in there or not. So, and this is basically everything that we need as far as I understood. So, because we know that x determines the middle of the sprite. So that means if the cycle time, from the cycle time we can find out basically which is the corresponding CRT position, right? Because this happens every millisecond, or every, not millisecond, every one cycle is one pixel rendered. So therefore we can just start with just print out one single pixel, right? Just begin with something that doesn't do much, but at least shows us a little bit how it could work. So for every time we are called, we basically just print out a pixel, a point. So, but now if we know, for example, that our cycle time, that we are at the end of a cycle, so if cycle time mod 40, so after every 40 steps, basically we need to make sure that our cycle time -1, because we start with the cycle time 1. Yeah, so we basically get the rest operation, so, or not the rest, the reminder. So, and this allows us to cycle from the values from 0 to 39. And this should allow us to make the decision, okay, we have now reached the end of our line, and then we basically just do a print line. So that we know, okay, this is now done. No, we are not done with that. So let's see what happens when we just render our pixels. So in the end, we should have then a couple of cycle time x. We should only have basically 2 or 5, I don't know. Let's see how many. Okay, this doesn't look completely right. So because this is a leading one, this is definitely not correct. Okay, then we do it something like that. Oh, this doesn't change. Shouldn't change at all. What is our cycle time at this beginning? Cycle time is 1. Okay, so cycle time starts here and is always 1 at this time. So it starts with 1. Okay, and then we need to calculate the position, pixel position. This is maybe the problem. So for the pixel position, the pixel position is now something that is changed by 1. pixel position is equal cycle time -1, and this then mod 40, right? Because cycle time is 1 based and our pixel is 0 based, therefore we need to reduce it by 1 and then map it again. Okay, and then now we need to figure out if x is in, if we should print a hash basically because the sprite is in there or not. So this is easy to accomplish by comparing our pixel position with the position of x. So x is the middle of the sprite. So therefore, if pixel position is less than, is equal x, then we are in the middle of the sprite. If it's x -1, then we are at the left, and if it's x +1, then it's the right part of the sprite, right? So therefore, we can just check if it's within those boundaries, and then we print a hash instead of the dot. So if pixel position is larger equal than x -1, or pixel position is smaller equal than x +1. Yeah. These cases basically we know. Oh no, if it's larger and this is not in this case. So basically where we are right from the, this is basically just a condition that checks that we are within the sprite. And if we are in the sprite, then we print out the hash, and otherwise we just print the dot. Okay, run now. Okay, this looks like some, I would say, like some characters, right? These look like an E, a G. So E, G, J, B, G, C, F, and K. Yeah, I think these should be it. So let's try. Maybe we are already done with our solution for today. Let's see. Yes. Wow. This was a nice one. This actually worked quite well. So, good. So, yeah, then we are through for today. I thought about maybe in the end do some revisiting of all those solutions. So with all the things that we learned in the end. So if you think that might be useful to start a discussion about those solutions and maybe come up with better ideas. So for example, for the this puzzle yesterday, I think we could simplify it quite a lot by getting rid of all this grid that we implemented. But if you think this would be useful, just drop a comment or something like that would be helpful. And but I think maybe after the calendar we can continue looking in these things and maybe even start doing the calendar in a different language, or we will see. Okay, so far everyone, have a nice weekend and talk to you tomorrow. Bye.